All right, for our next set of topics, we're going to talk about circular motion and gravity. The forces necessary to make something move in a circle have certain attributes which we're going to discuss. And we're also going to discuss a more general formula for gravity. Okay? So in this video, I'm going to start with the gravity formula, and I'll leave the circular motion analysis for another video. Okay? Now, you've already seen one equation for the force of gravity. The force of gravity is equal to mg, where m is the mass and g is the acceleration, free fall acceleration, given by approximately 9.8 meters per second squared. Now, this equation is true, but it's only true in a certain context. It's not true in all cases. Let me give you a situation where it's not true. Suppose you were on the other side of the universe. All right, clearly the Earth wouldn't be sucking you back to the surface, right? If you were far away enough from the Earth, you wouldn't feel you'd feel a negligible amount of gravity from planet Earth, okay? So clearly, the force of gravity gets weaker as you get far away, okay? And that's what we need to account for. If you're close to the surface, and I'm sure that probably 99.999% of you will spend your entire lives close, within about a mile or two of sea level, okay, unless you happen to be an astronaut someday. So most of you are going to spend your time pretty close to plus or minus 1 or 2 miles from sea level. In that situation, this gravity formula will work, okay? So you can see why we didn't belabor the point earlier, okay? This is adequate for most of the situations that you will care about. All right. However, if you're talking about satellites and other planets and other situations where you are farther away from the Earth, well, then we have to adjust the formula. Okay? The formula that I'm going to give you, the general one, is the following. The force of gravity is equal to G, new constant, m1, m2, divided by r squared. And this is the force not just for planet Earth, but actually between any two masses. Okay? So if I have 2 planets, 2 moons, 2 asteroids, 2 Tonka trucks, it really doesn't matter. One of them we will call mass 1, object 1, mass 1. One of them we'll call object 2, mass 2. And we'll define the distance between them. We'll call that r. Okay, and so you plug that into this formula, and that'll give you how much each of the masses is being pulled towards each other. Okay, that's the direction, because the gravity is always attractive. It never repels like a magnet may do. All right, and then the G, that's a new constant, that's equal to 6.67 times 10 to the minus 11. Newton times meter squared divided by meter squared divided by kilogram squared. All right, and so you'll multiply by that constant. That constant's always the same as far as we know, no matter where you are in the universe. That the capital G constant is always that number. Okay, this is called the law of gravitation, or Newton's law of gravitation, and the capital G is called the gravitational constant. Okay, and so for any situation where you have 2 bodies, you can use this formula. Now, sometimes I tell people that every pair of masses has gravity, and I had at least one time that I could remember, I had somebody that thought, no, I don't believe it, you know, that everything, are you saying that every time I meet somebody there's a force between us of attraction? Okay, I'm not talking about, you know, an amorous force, but a physical force. And anyways, I had somebody thought that sounded a little bit new agey, but it's really true. It's just that the force is unbelievably weak. All right, let's do a calculation. Let's say you're standing next to another person and you're a meter away. Okay, let's calculate the force of gravity between you two. All right, now just to keep things simple, let's say that you both have a mass of 100 kilograms. Okay, and so let's say we said that you're a meter away, so that means R is 1 meter. All right, and so let's plug it into our new powerful gravitational formula and see what we get. So we're going to get 6, I'll do it in the bottom right, let's see, how about black. So 6.67 times 10 to the minus 11, and then 100 times 100, so 10 squared times 10 squared divided by 1 squared. That's 10 squared times 10 squared. That's 10 to the 4 times 10 to the minus 11 makes minus 7. So, yeah. So the answer is 6.67 times 10 to the minus 7 newtons. Okay? Or, if you want to be fancy, you might say about 0.67 micronewtons. All right? So basically nothing. All right? That's a pretty wimpy push. That's why we don't stick to walls as we walk down a hallway. All right? Now, here's an exercise I would like you to do now. So let's calculate what the force of gravity would be for a 1 kilogram object on the surface of the Earth. All right, let me go to a new whiteboard since I'm running out of room here. And I will copy the new force of gravity formula. Okay, and I'll also copy what the G value is, 6.67 times 10 to the minus 11 Newton times meter squared divided by kilogram squared. Okay, so we said we want to know for a person standing on the surface of the Earth. So let me make a picture. You may remember I'm a big fan of making pictures so that you don't try to have to hold stuff all in your head all the time. Okay, not a person standing. I said it was some little stick or something. So I'll put a little rectangle there, and it was 1 kilogram. All right, so we're going to use this formula, obviously. So you're going to do, the G is not going to change, 6.67 times 10 to the minus 11. And for the mass of one of them will be 1, the 1 kilogram. It doesn't matter if it's M1 or M2. And then the other one will be the mass of the Earth. Okay, I will leave it to you to Google for the mass of the Earth. I'm going to give you an exercise to here in a few minutes. Now, what do we use for the distance between both masses? Now, because the 1 kilogram mass is on the surface of the Earth, it's touching, you might think that there's no distance between the Earth and the mass, okay? But I ask you for R, calculate it as the distance center to center distance. All right, so actually you want to know the distance from the center of the 1 kilogram mass to the center of the Earth. So I'll draw a red stick like that. And clearly that is going to be, the R is going to equal the radius of the Earth. Whatever that is. Okay? So we're going to have some number at the bottom squared, and I want you to Google for that. That's going to be the radius of the Earth. Okay, and I'd like you to stop the video and Google for those two numbers, plug them in, do this whole multiplication on your calculator, and tell me what you get. And then I'll tell you the answer in a few shortly. Okay, so do that now. Okay, so if you plugged in the correct Earth mass and Earth radius and you did everything correct on your calculator, then you should have gotten 9.8 newtons. Okay, now doesn't that look familiar? Does that remind you of anything? All right, the 9.8 should remind you of the little g that we've been using before. Okay, now suppose that instead of using this formula, suppose you instead use the old formula. The old formula, remember, was mg, little g this time, as opposed to capital G. So that would have given you 1 times 9.8. So notice that the new formula gave you the same answer as the old formula. All right? So now this is a good thing. It would be very bad if I was giving you contradictory formulas that gave you different answers. Okay? So we would have demanded, of course, that a more general formula would have agreed with a more specific formula. Okay? So what I'm saying is this, I'll put it in a box, this new gravitational formula reduces to the old one near the surface of the Earth. Okay? It'll give you that m times little g. But as you get farther away, that's when things change. All right, let's talk about how things change. Notice that there's an r squared in the bottom. That's called an inverse square dependence. Okay, watch this. If I double the distance, my distance from planet Earth, how much weaker is gravity? You might think that if you're twice as far away that you have half the gravity, but because of the squared term, you actually have 1/4 the gravity. Okay, work it out, make up some numbers, pick one r that's half as big as another r, work them both out, you'll see that gravity is 4 times weaker when you're farther away. If you were 10 times as, if a certain satellite was 10 times as far away from the center of the Earth as another satellite, it would actually have 100 times weaker gravity. Again, because of that squared, the inverse square dependence. Okay? Now, as a little exercise that I'll leave with you, you might consider finding the gravity on the surface of the Sun and several planets, Mercury, Mars, Pluto, to get some practice with this formula.